Hey everybody, it's Brad from Roboflow, and I'm here for our second YouTube live stream. A few weeks ago we did a blackjack demo, and today, in commemoration of Sunday football, we're going to be doing a football-themed live stream. So without further ado, let's dive in. All right, so you might be wondering what football has to do with computer vision, or potentially even what computer vision is at all. So for a brief preface, computer vision is giving software the sense of sight. We all know that our devices have cameras, and I liken that to our eyes, but they feed out pixels just like our rods and cones in our eyes feed out like raw information. And it's up to our brains to interpret what those that raw input is, and that's what computer vision is, except for computers. So it's about taking those pixels and turning it into useful information. And it can do everything from monitoring oil pipelines to telling you what's in a sushi roll from your cell phone camera. And in fact, we have users on Roboflow that have done projects doing both of those things. And so as a way of background, Roboflow is a software company that makes computer vision easy to use, even if you're not a computer vision expert or know anything about machine learning. We cater specifically to developers, so if you know how to do a little bit of code, you can use computer vision with Roboflow. And so today, we're going to walk through making an entire project. Fingers crossed, we're going to be doing this live, so you'll get to see the entire thing, soup to nuts, warts and all. So hopefully we get something working by the end. And the project that we're going to be doing today is a app that's going to help coaches, football coaches, analyze game footage. And this was inspired by one of our users, which I'll share quite a bit about as we go through. We're going to be making a very simplified and like dumbed down version of this on this live stream today. But this user actually has made a really robust version that I'll show you kind of the inspiration for what we're working on. All right, so I'm going to dive in, and the project that we're going to be using today is actually shared by a user named Scott Bronkema, and he shared this on Roboflow Universe. And this is our community website where anybody can share their computer vision projects for others to use as a starting point. So if we didn't have this project shared, we'd be right now talking about how we were going to go out and collect a whole bunch of football game film and go through and label all of the players in that film, and then train a model and basically spend weeks and weeks prepping for what we're about to do in this live stream. But amazingly for us, Scott has done all that hard work for us and shared it publicly with the community. So we're going to be able to start from his ending point with this model and be able to get up to speed within just maybe an hour or two. So on Roboflow Universe, we can dive in and look at what this data set that Scott shared was. And he's gone through and he's taken a whole bunch of game footage and sliced it up. And then on each one, he's labeled the players. And so what his model does is use these as essentially flashcards where you're training a computer to look at a bunch of these images of football players and learn where those different players are and which position they're playing. So he's got a variety of different camera angles and a bunch of different football fields, people in different uniforms and all of that kind of stuff. And so if I hover over one of these, I can see this is labeled as a defensive back. The quarterback's over here. This looks like a skill player, so like a running back or a wide receiver. And by looking at many thousands of these photos and going over those flashcards thousands and thousands of times, we can train a machine learning model, a neural network, to basically replicate this output on new images that it's never seen before. And so that's what Scott's done for us. He's actually already trained a model here, which we can just use with Roboflow as a piece of our program. And so we're going to use that in combination with a few other things to build something hopefully pretty cool today. So there, I'm going to pause and cover a few pieces of, I guess, introduction and house cleaning. So first of all, we're live streaming on YouTube right now. This is the second live stream. If you're enjoying this format, please be sure to give the video a like to give us a boost in the YouTube algorithm. And also, if you're watching right now as I'm speaking, please go ahead and share this on social media. It'd be great to get a whole bunch of viewers on this YouTube live stream and get a bunch of interaction. And speaking of interaction, we are going to be, or I am going to be watching the YouTube comments to see if anybody is around. So maybe let's do a test of that, and I can answer your questions, or you can leave comments, and hopefully if I get stuck on any of the coding components, you can help me get over the hump. But could you give me a just thumbs up in the chat if you are here and following me? Audio, video is good, and all that stuff. It would kind of stink to get to the end of this live stream and realize that I forgot to turn on my microphone or something. So I'm going to pause and look over here at the chat. I just said hi, and let's see if there's anybody here. It looks like we've got about a dozen viewers so far. So yeah, is anybody out there? Give me a thumbs up or say something in the chat if you're here. And maybe it'd be fun to hear who you are, where you're from, whether you've used computer vision before, and anything like that. We can maybe start a conversation around that as I'm coding. So I see a couple thumbs up in here. I actually see Scott, the user who shared this data set and model in the chat. Hey Scott, thank you so much for hooking us up with all of this amazing content that we're going to be able to share. That is actually a great segue to the next thing that I wanted to show you, which is actually Scott's output. So I'll switch back over to my laptop view over here. Okay, so we just checked out the model, or I guess the data set. I can show you the model in just a second. But I want to point out the user who shared this, who's a football enthusiast and has been working on this project for a number of years. So Scott Bronkema actually brought this to our attention, and we've been having a lot of fun chatting with him. If you go to his LinkedIn profile, you can see a whole bunch of his videos that he shared about the creation of this project and everything about it. Highly encourage you to connect with him. Scott's a real cool dude, and we're excited to have him as part of the community. And in fact, we just, right before launching this live stream, published an in-depth study of Scott's project on our blog, which at the end of the stream, I'll make sure to put this into the notes below. But if you go to blog.roboflow.com, you should see more information about Scott's project. And as I said, Scott's project is way, way more in-depth than we'll be able to build today. But here's kind of an example of what it does. So you can take a snippet of game film, and using his program, you can get an output of where those players moved. So this is a great teaching tool and learning tool for coaches to help their players get better at the game of football and hopefully win more games. You can read all about how it's done. There's even some GIFs and some video about the UI behind the program included in here. I thought it was really cool getting a sneak peek of what that looks like behind the scenes. I'll see if I can get back in here and find the UI that I saw that he posted. But you should definitely check out this post and see what Scott does. Because it basically lets you highlight the certain players and then see as the video is going kind of where they're going and how it's doing everything. But this is an example of computer vision in the wild, whereas we're going to basically be making a little bit of a hack today that's more of a demonstration. So without further ado, I will dive into what I'm planning on working on during this live stream today, and we can check out where we're shooting for. So a bit of inspiration. If you don't know much about football, basically there's two opposing sides. They line up on a line of scrimmage. The offense has the ball, and they're trying to get it towards the end zone on one side of the field. The defense is trying to prevent them from doing so. And so usually, if you ever heard somebody say, talking X's and O's, that's how coaches will talk about how they draw these things up on a whiteboard. And so they'll draw out where the different players are going to start out, and then have arrows of where those players should run. And where the people should block and what they should do. And so this is a lot of what studying game film is about, and this is essentially what your playbook is about when you're doing computer vision stuff. And my inspiration behind this was actually playing some video games and being able to see how they translated these playbook things into an overlay over the top of the football field. So you can see that this guy, I think this is the running back, is looking in this direction. He's going to run in this direction. And then also when you're watching football broadcasts, the announcers sometimes are marking up the play to explain to you what happened on the instant replay. So oftentimes they'll circle players and draw arrows and call your attention to things. So in this wide receiver ran this way, and then this cornerback like went this way. And so I was thinking it'd be awesome if instead of having to have like Joe Madden annotating it for us live, we could just feed in a video and get out some sort of visualization like this of what happened in that play. So you can imagine this either being used in the film room by coaches or by like a TV crew. If you could essentially have your crew that snipped the instant replay, just click a button and it would put an overlay over the top of it of where those players ended up going throughout the play. Maybe if you knew what like the playbook was, you might be able to have it automatically identify if a certain player went the wrong way or something like that. But it would be really cool to be able to automatically use computer vision to start to process some of this game film, especially since we have hours and hours and hours of it being created, not just in professional football, but also college football and high school football now. A lot of that game footage is recorded, but those high school staff doesn't really have the same resources as an NFL team. So if we could bring some of these advanced analytics and stuff to the high school realm, maybe those players would be able to get better quicker and we can improve the game. So that's kind of the inspiration. And now I'll talk a little bit about what I'm sort of planning to do in this live stream. So at a high level, the idea is we want to take in a video clip of a play and we want to output an image of that visualizes in some way, what happened in that play, where the players went. So the pieces in between are what we're going to be either using if they're already created or creating if they're not. So basically, we're going to take in the video and then we're going to do two things. First thing, we're going to extract the first frame of the video and use that as the starting point for the visualization. So normally the players will kind of line up like this, or I guess line up like this. And that's what we want to use as the starting point and then draw the arrows over the top. So we're going to take the first frame of the video and use that as like the base of our visualization. And then everything else that we're going to be doing is going to be about finding out where we should draw these arrows and then eventually drawing the arrows over the top of that first frame of video. And okay, so that's the easy part, right? We should be able to pull that first frame of video, no problem. I think I might use ffmpeg for that, but again, we're doing this live, so you're going to see this warts and all, and probably going to be Googling quite a bit of things here and maybe even asking the audience for help. The other flow is the computer vision flow. So we're going to use Scott's model that he published on Roboflow Universe to identify, take in that video, and from each frame of the video, identify where those players are. So if you recall, when we looked at the images in this data set that the model was trained on, it learned how to take in a picture and identify which ones of these are which types of players and draw a box around them, essentially. So the first step is we're going to take each frame of the video and put it into Scott's model and get out that data back, which then we're going to take to the next step of the process, which is going to be object tracking. So I'll talk a little bit about this in just a second, of the difference between object detection and object tracking. But at a very simple level, object detection is telling us, taking a frame of video and saying there's players here, here, and here. Object tracking is taking a video and those detections from each frame and matching up and saying this detection of a player is the same player as a frame before. And so that's going to let us take this like stream of detections and turn it from many individual detections into one that is like correlated over the temporal frame, so that we know where to draw our arrows versus having like a whole bunch of boxes and not knowing what to do with them. And I'll show you an open source project that we've come out with that will let us do that. So the end result of that is that I want to take those basically like tracks of where the players are running throughout the play and serialize them into something that I'm going to be able to use to visualize those arrows. So this is something that we're going to have to code. The open source repo that I'll show you, the output of it is a video that kind of like visualizes the boxes and then numerically numbers like this player is tracked throughout time. But we want to, instead of having a video output a video, first output something that is readable by a computer program, and then use that to output an image instead of a video. And then the second thing that we're going to code today is the actual visualization. So once we have that data serialized and we have the first frame, then we'll figure out how to draw those arrows on top of things and end up with our image at the output. To talk a little bit about where we would go from here. So what we're going to be doing is essentially like the R&D of proving out that this works. We're gonna use a live video or a actual video from YouTube to do that. It's essentially a contrived test set of images that the model has never seen before. So we'll see how that goes. But after this, you do something like creating a front end where you can clip a video into a play, and then it would wire all this stuff up and be able to output that image. You'd have to deploy this onto a server somewhere, probably. Although I'll show you how this interacts with the Roboflow API as we go through things. And then we'd have to come up with a business around it, maybe. But if you wanted to do this in real life, like I said, maybe just contact Scott, because he's done a lot of this hard work, and you could get up to speed a lot quicker than building it yourself. But the purpose today is to kind of learn how we would go about a project like this, so that maybe you can apply it to something else, maybe not football related, something more close to your job or profession that might be useful to you in your day-to-day work. Okay, so I'm going to pause there for just a second and take a look at the chat and see if anybody had any questions or anything before we get started. Looks like we've got more people saying that the stream is okay. Somebody's tuning in from England, and they used computer vision in their postgraduate work. That's pretty neat. And somebody else is asking when there's a full explanation of the YOLO v5 co-lab coming. Check out actually our other videos. Jacob has done one, I know one how to train YOLO v5 video at least, because it's our most popular video on our YouTube. But we're going to do more YOLO v5 content as well. We actually just announced a partnership with Ultralytics, the creators of YOLO v5, where there's a deep integration between Roboflow and YOLO v5. We're the official labeling partner for them, and also there's some deep integrations that are coming soon that we're pretty excited about. We really like that machine learning model, and they share our vision of bringing computer vision to every developer and making this something that is not just for experts, but for domain experts as well. Okay, so without further ado, let's look at how we're going to do this part of the flow. So first, we're going to need to take a video and do inference with that model on it. Luckily, Roboflow has an open source project called Video Inference that's going to do this. And so you can feed in a video and it will output the detection of a model on that video. So to use this, you would just go to this repo link, which again, I'll add below. But if you go to the Roboflow AI GitHub, you'll be able to find this as open source. You would clone the repo, and then there's instructions down here for how to use a trained model. So the model that we actually want to use is this football model that Scott uploaded. So that's football player detection / version 2. And so if you follow the instructions and you put football player detection /2, feed in a video and put what you want it to be visualized in, and then there's a whole bunch of other settings that you can do, you can get a visualization. So let's start out by doing that. So I actually already found a good video that I want to try. And so what do I mean by good? Essentially, when thinking about how I wanted to visualize a football play, there's a couple of criteria. So most of the football broadcasts that I could find had a camera operator that was moving the video camera around, which didn't seem like it would be very easy to be able to use that as the input to our model, because we're going to get pixel coordinates on the screen, and if the camera is moving around, we would have to figure out how to offset that so that we have the actual coordinates on the field that the player is going to. Scott solved this in a pretty cool way in his project, but we weren't going to have time to do that in ours, I don't think. So and I went and I searched for fixed camera, and I found this stationary camera video feed of, I think, a high school football game. And then I went through and found a play that looked like it would be fun to visualize. So I'll just go ahead and hit play. I've queued this up to the point at which the play is about to start, and I'll stop it when it ends.
Receiver left, 3 to the right toward the wide side of the field. Blitz coming. Trouble, but getting out of trouble that time is Kizzy. Going to run with it. 35. Cuts right. Kizzy to the 30. Kizzy with a first down.
Okay. So this guy, I don't know if you could see that very well, but this guy has the ball. The quarterback was back over here, and it looked like his track ran kind of like this, and then all of the defensive players kind of ran toward him. So if I go back to the start, hopefully it saves my place. Okay, so this was the starting point. So if I feed in this video, this is essentially what I want to start with, and then I want to draw arrows for where all those guys go. So if we watch this one more time, let's see if we can figure out where the guy with the ball that ended up here started from. Looks like here. Well, maybe our model is going to be able to tell us. I couldn't really follow him. It looks like he cut across the field and went up here. So a couple things about this video. I liked that it was static so that we can essentially crop in and visualize that stuff. The downside is that by cropping in on this, it looks like it's going to be pretty low resolution. If you notice, Scott's images were all pretty high resolution. It looks like they were like HD from like a television broadcast. So hopefully these cropped videos are going to work okay. But we'll give it a try. The other thing to recognize is that it looks like there's going to be players on the side, or coaches and stuff. I'm not sure how that's going to affect the model either. And the last thing is, I think we're going to need to crop this down. This is like a 4-hour video, so we're going to want to crop down. So the only prep that I've done for this was finding this video, and then I did those things. I cropped down, or I trimmed down the video to the play, and then cropped it, and then we'll see kind of where I went from there. Okay, so if we want to use this Roboflow video inference on this video, I went ahead and used a program called YouTube DLC, which I have pulled up here. So if you clone and install this program, you get this Python package that gets installed globally, and you can download YouTube videos with it. So I did that to download the MP4 of this YouTube video. So if I open that up, we're going to see that it is a 4-hour video that has kind of the whole game from this fixed camera position on it. I think if I was going to be using this as a coach, what I might do is, if I had a camera operator, instruct them how to zoom in and have like a static view of the play. So it might be, instead of like one camera angle for the whole time, I just want one camera angle for the play. Or maybe I would just like have them get a 4K camera, and then when I crop down, the video is going to be more high resolution. I'm not sure. It looks like this has some sort of fisheye lens on it too, which might not be ideal. But we don't have that luxury. We're using a YouTube video and a pre-trained model that Scott gave us, so we're going to do our best. So what I did was I cropped that down and or trimmed it down and cropped it. And if I switch over to my other screen, I have the commands that I did to do this. Okay. So I forgot to mention, I created an open source repo for this. Right now, I initialized it as empty, and then I've been adding to it, and I'll publish all of the code for this project at the end of this video stream, and link to it below. And so you should be able to follow along and do this with your own project and your own videos, hopefully, because we're going to be doing it all live. You should have everything. So To download the video, I used YouTube DLC. It accepts a format parameter, and so you can pass best video, and that's going to download this in the best format possible. And then I pasted in the YouTube URL. This took like 15 minutes to download. It was a 3 gigabyte video, and then I had that 4-hour video. I then on the YouTube stream went and saw where that play started and ended that I wanted to use as the example. So that was at 2 hours and 52 minutes and 56 seconds. So ffmpeg is a really nice video editing command line tool. It's kind of opaque though. Usually when I want to use it, I have to look on Stack Overflow for what all the parameters are and what order they're supposed to go and how to use them. So for this one, I looked for trimming a video to a certain timestamp and cropping a video to a specific bounding box. So it takes the input of this video, which was downloaded from YouTube DLC, and then it takes the amount of time. So on the YouTube clip, I looked and timed that the play takes 12 seconds. So it starts at 2 hours and 52 minutes and 56 seconds and went till like 2 hours and 53 minutes and 8 seconds or something like that. So I put in 12 seconds here. And then I wanted to crop it down to get rid of all of that extraneous information around the play. And here I just trial and errored until it seemed like I'd cropped it down right. If we were doing this in the real world, I think it would be great to present the user with like a ability to draw a box or something around the area of the field that they want to crop to. Or maybe, we could use the output of our model to be auto cropping or something like that. But for me, we're only gonna do this one play. And so I just kind of hand tuned this and cropped the play down to that, and then outputted it to a file called footballplay.mp4. And so if you noticed, when I had this pulled up, I have footballplay.mp4 here. It got it down to only 675K. And if I hit preview on here, this is what I cut down, and this is that play that we looked at. You can see it's really pretty low resolution, which is unfortunate. Okay, so let's see. Looks like that player was this one, maybe right here. That's going to end up getting the ball. Oh, I think it's the quarterback that just scrambles the whole way. So let's go ahead and open this in Photoshop. Oh, I think I might want to... Okay. I'm going to take a screenshot of the starting point, and then let's open that in Photoshop and get an idea for what it is that we're going to be aiming towards, just so that we have kind of a picture in our mind. I'm also going to pause and check out the comments again while I do this. Oh, nice. Scott has a good tip of YouTube all 22 coaches film for good videos to use. If this, he said he screenshotted some of that from Twitter, from NFL Game Pass, which is a paid service to get higher quality video. Hopefully this will work good enough for our demo purposes. If not, we might call an audible here and try and get better video later on and go back through our process if this crappy video that I got doesn't work. And it looks like some other people tuned in a little bit later. If anybody was on the stream at the beginning, it would be really helpful if you could answer some of the questions that they had from the beginning of the stream. Would really appreciate that. Okay, so here we are in Photoshop. I'm going to crop down to just the play size. So I think what we're essentially going to want to do is have some lines, and I'm going to just draw them on here by hand. So it looked to me like this guy, let's see, let's pull it up again. So the quarterback kind of comes backwards and then runs this way and then that way. So it's maybe something like quarterback's going to go backwards, forwards, something like that. And then let's see, what do the other players do? So this guy just kind of goes to the right. That wide receiver takes a right turn, ends up blocking. So this guy goes like that. Let's see what these other two wide receivers are doing. So it looks like they just kind of like run like this and something like this. So this is just kind of like what I'm thinking in my mind is that at the end of this process, we're going to want these sorts of arrows that go like this. And the same thing for the defense, maybe in different colors. Not sure if we'll be able to tell offense and defense here. I know Scott's model tells us the players, but I think I might actually strip that information because of something that we'll see here in just a second. Let's see. It looks like this is actually going to be pretty busy if we're drawing all of these lines on here. I wonder if there's a way to only draw the important ones or to like figure out which ones are most important. For a given play. Like maybe the player that runs the farthest distance or a player that stays on screen the whole time might be more important than one that doesn't, although I think most of these players are gonna, I don't know. But basically what I'm thinking is like if these linemen aren't really moving that much, maybe at the beginning, then we can ignore them. I don't know. Just kind of brainstorming what potential pain points that we're going to run into here and thinking about in my head how we're going to code this. Because like I said at the beginning of the video, we're doing this live, have not done this before. Okay, so let's let this percolate in our mind a little bit and see what the model is going to give us for this video. So I've actually gone ahead and used that Roboflow video inference library to get a visualization here. And basically all that I had to do was get my Roboflow API key from the app, which actually on that Roboflow Universe page, if you click on, I'll bring it over here. If you click on use curl command, it will give you that API key within there. And so then you put that in an environment variable and the infer script is going to use it. I told it that I wanted the input and output to be 30 frames per second, which was what this video we got from YouTube was. I'm going to run it in parallel on 50 different machines. We're going to use Roboflow's API to run Scott's model. I tuned the confidence by doing this a couple of times and put it down a little bit just to show us more boxes. And then I drew a stroke of 2. And so when I ran that, it took this input video and gave me an output video with the boxes of the players. And you can kind of see the players that it's detecting are changing. Like sometimes it changes what they're detected as, or sometimes doesn't detect them at all. And so I think that's going to confuse our detection model a little bit. So like even the quarterback there disappears and then reappears, and there's like a yellow versus pink, which I'm not sure which classes those represent right now. But I think what I want to do is just map these all to player, so it doesn't matter which one they are, and then try and keep track of the ones that are the same player. Looks like it's also got some of the referees in here too. We might try and tune this a little bit as we go through. But it does look like it See, it loses track of some of the players, though. Okay, so I'm wondering if what we should do is take the object tracking code and have it use like the first second or two of video to determine which players it's going to track, because I think this does a pretty good job of, like, if we run 30 frames through this, maybe that'll tell us who the important people are, and then just track those, so that then we're not trying to identify some of these other ones, like the linemen in the middle here that sometimes get detected. Okay. So anyway, this is the output of the raw object detection model at 20% confidence. And this is outputting a video. But we can also get the raw information from it. So object tracking is a little bit different. Let's look at what object tracking is compared to object detection. Okay, so we were just looking at the Roboflow video inference repo. Instead, let's look at the Roboflow object tracking repo, which is called zero-shot object tracking. So in contrast to the video inference, object tracking tries to determine which boxes are the same over time. So you can see that this one is Shark 30 for most of the video until it gets misidentified as it goes back into the fog. This one's Shark 14, but it's kind of a fish. This is fish 1 mostly the whole time. But essentially, it's determining, like, this is fish 1, this is fish 8, and it stays that way based on the contents of the bounding box over the course of the video. And the way that this works is with a model called CLIP, which is a multimodal model, but essentially it is a very general purpose classification model that learns things like attributes or abstract concepts about things and can use those to do image similarity. And so the basis of this model is that across the frames, each box is being compared against each of the boxes from previous frames to determine which ones are most similar, and to use those as the same sort of detection and identify them as the same object or the same instance of a detected object. And again, this is an open source project that we came out with, which you can read the documentation at, and I will link to after the video. And just before the video, before we started the stream, I kicked off a job using this code. So I took it looks like I ran the wrong model. I took that football play MP3 and just ran it through with the default settings. And I think this needs to be... Oops, sorry, on the wrong screen. So I had accidentally used the playing cards model here, which was from the documentation, but needed the football player detection one. And then I ran that through this script. And I haven't looked at this output yet, so we've caught up to my prep work, and now we're going into the wild, wild west here to figure out what we're going to do. So I'll scroll back up to this model output. Okay, so I had fixed this to use the Roboflow object detection API to use the football player detection model with my API key. I'm going to blow this up bigger so that you guys can see it better. So this video that we have has 359 frames, and then on each frame, it ran it through and detected what came out of the model, and then each of these boxes it's going to store in memory and compare on each additional frame. So it looks like as we came through, we're tracking 16 players. which is interesting because there should be 11 players on each side, so we should have 22 total, but I know that the model only detects certain players. So no linemen, which is interesting. And then later on it drops down to only having, oh, it goes up to having 25 things tracked. Okay, so like I said, I haven't seen the output of this yet. This is kind of the in progress of what happens on the as it runs through things, and I'm running this on my Mac, which means that this does not have access to my GPU, so it's a little bit slow to run this. But the results of this get saved into a video, just like the video inference script does. So if I open this, I've got the output, and we can see what's going on here. Actually, it does a pretty darn good job. So that skill, let's take a look at skill 6. He stays skill 6 all the way through, but here, okay. Oh, except for it thinks that he's... I wish I had higher resolution imagery to feed into this model. I think it would do a lot better. And this is also using the default confidence too, so I think I'm going to want to bump that down. Okay, so let's dive in and start hacking away on this to get a better visualization here. So the first thing that I think I'm going to do is I noticed that it was kind of flip-flopping between what position it recognized as the different players. So I think I'm going to rename them all to player and then just track player numbers on here. And then maybe we can back out of it later if we need to, just like track the QB or something. And then I'm going to adjust the confidence levels to be the same ones that we had in the video inference one because it seemed to track more players that way. So let's see how to do this. So I think I've got this guy cloned. So this is the video inference, the object tracking library that we had pulled from GitHub. And the main file in here is clip object tracker. So word of warning, I did not code this. So we're going to be together figuring out how this works. Pause and check the chat too. Cool. If you guys have any comments or questions, feel free to leave them in the chat. It looks like there's nothing that I need to respond to at the moment. But I might be asking for your help here in the near future as I struggle bus with some of this code. But we shall see. Okay. So first thing I want to do is update the confidence. So let's look for that. Oh, it looks like this takes arguments. Okay, first thing I want to do, actually, I recognized that this model took forever, or this took forever to run. So let's generate a new version of this. bigger so you can see it. So I'm back inside of this guy, and I've got my football play.mp4, which that was this snippet over here that we generated it with. But let's go ahead and let's take less time from that. Let's maybe go like 6 seconds, and then I'm gonna Google. I want to drop like 3 out of every 4 frames, because this had like 350 some frames. So if I cut it in half in terms of length, and then I cut it in 4th by reducing the frame rate, we're gonna go down to 45. And then that way, if I only have 45 frames, then when we're messing around with the clip stuff, it'll take like 8x less time that we're waiting for it. Okay, let's try this one. I'm not sure if this is gonna work. So I think we need the filter v FPS equals 30, but I'm gonna cut that down to 30 divided by 2 divided by 2. That's not right. 30 divided by 5? 6 frames per second? Looks like it's a comma that I need instead of a semicolon. Let me go for 5. Yeah, we'll see how this goes. Ooh, I don't want that. I want football play short. That seemed to go too fast. I don't think that. Perfect. Okay, so if I run that clip, 0-shot object tracking again. Oh, you know what? I bet I need to copy this into the right spot. Okay, so let's run clip again, this object tracking thing again on this other video. And just see what we get and see how many frames it sees. It should see like 10x less frames once it starts running. Wonder why this is hanging so long. I've got my Python environment set up. Oh, I wonder if this is... Okay, so yeah, 36 frames instead of 360. That's good. Okay, so I'll let this run and we'll see what we come up with. And as I do that, let's go ahead and start editing this code. Oh, you know what? Let's make sure that this confidence comes through. Okay, so it passes in the confidence. That comes from opt, and opt comes from down here. So these should work. So it looks like our object tracker has done 32 of our frames. So let's not kill it to change this, but once it's done, we'll see the results. Or actually, once it's done, I'll kick it off again with a different confidence, and then we'll see the results of the last one. So I'm going to come up here and do... Is this supposed to be 0 to 100 or 0 to 1? Are there other things in here that I wanted to change? What did I do in my snippet? Stroke was 2. Thickness was... You know what? It looks like they don't use those equals here. And then the last thing... Is there a way to turn off the text? Oh, I guess we need the text on this one. It seemed like it was getting in the way, though. Oh, well. Okay, so I'm running that. I'm going to open this up. It outputs the runs into run/detect. Looks like it was run 10, so let's open that. Oh, no, it's runs 11. No, 12. Oh, shit. Which one's which? Yeah, it must be 12 because that's from today. Okay, so here's the... Oh, runs 12 is the one that's in progress. Runs 11. Well, hopefully the one with the lower confidence is going to have bounding boxes on more of these frames because it looks like it didn't track them properly. We might have to tune some of the tracking stuff now that I dropped these frames. Let's see where we're at on run 12. 27 out of 36. This would be a lot faster if I had a GPU that was supported. But again, running on my MacBook CPU right now, so it's pretty darn slow. I wonder if it'd be worthwhile to boot up a GPU machine to speed this up during the live stream or not. Okay, no, it still lost that guy. So the one that I'm keying in on is this wide receiver at the bottom, just because he's like all on his own, and it's very clear that he's getting lost. Oops, this guy right here. Which I wonder if that... Interesting that... Okay, so... I think... So, see how that switched him from skill number 9 here to DB number 2? I think this is that problem I was talking about with the difference in the classes tripping up the object tracking. Because if it switches the class, it's not able to... It assumes that things can't change classes. So I think let's just remap these all to player to start out with. Do as I say, not as I do. This is gonna be hacky. I would not recommend doing it this way, but hey, we're on a live stream. We're gonna hack this not particularly well. Let's see. All right, I think right here we're hacking into the prediction function, and this is already going through and remapping stuff, and I'm just gonna override and clobber it and call everything player, and then let's run the same object tracker with the same settings and see if that did anything. I'm gonna look at the comments since this is gonna take a second to run. Oh, it looks like there's some of my team members at Roboflow calling out some stuff here. So Jacob commented on the frame reduction to speed up object tracking dev speeds. Thanks, Jacob. The other thing I could do is boot up a GPU, but I'm kind of lazy, and that seems like a lot of hard work right now. So maximize laziness equals minimize work. Joseph Nelson, my co-founder, says, can you talk through why you're concerned about checking a few different confidence levels in the object detection step before passing to clip for object tracking? Yeah, so the reason that I'm playing around with the confidence is you want to give the object tracking model enough information to work off of, but not a bunch of noise that's going to confuse it. And so usually there's like, heuristically speaking, a decent confidence level that you can look at for a model that gives you a good trade-off and balance. If you put it at 100% confidence, that means like only show me things that the model's 100% certain of, which is almost always going to be 0 things. It's always going to pretty much hedge its bets and say like, I'm 99% sure this is a player, or 99.9% sure this is a player. And on the opposite side of the spectrum, if you said, show me anything that is 0% confidence or higher, there's going to be thousands and thousands of identifications that thinks like, well, maybe this is a player that aren't going to be particularly useful. There's actually some interesting work being going on in the research community recently about being able to use those low confidence predictions and just passing in the confidence as sort of information to a secondary model. But we don't have that built into the object tracking stuff just yet. So trying to find a good balance that gives the model the right amount of information. And Jacob's making fun of me for hacking that class in the right way. Okay, so now we see that everything is a player versus having those different positions that came from the model. Looks like that didn't help. It's still identifying that player 13 turns into player 2, and is player 2 that guy? That's not good. Okay, cool. So, I'm gonna pull a Who Wants to Be a Billionaire card here, and I'm gonna dial a friend. So I saw that Jacob's in the chat. Let's give him a call and see if he has thoughts about what we should do here to improve this model, because I have some thoughts, but I'm not sure that it is the right course of action. So we're gonna try this live. I'm gonna call Jacob. Jacob, if you're still in the chat, your Zoom's about to ring. Jacob says in the chat he's signing on. While we wait for him to join, anybody in the chat have any ideas for how we should go from here? I'm a bit concerned with this, which is that it looks like our model isn't doing a great job of tracking this guy on the bottom frame to frame. Looks like it's losing him, and if we don't have him tracked, I just don't see how we're going to draw arrows on his pathway. But it's weird because the output of the model, let's see if I can pull that one back up. See, Jacob signed on here.
Hey, Brad.
Hey, Jacob, how's it going?
Pretty good.
Figured I'd call in the big guns.
This is exciting stuff.
Yeah, hopefully this is working. If somebody's in the chat and can let me know if they can hear Jacob on his end, and if it's not just coming out of my computer audio, that'd be awesome. All right, so Jacob, I don't know if you've been following the whole stream or not. So I'm at this point where, let's see if I can pull this up. It looks like we've got detections coming out of the model, but I'm not sure that they're going to be stable enough to get the object tracking stuff working. You have any ideas for hacks that I could try to trick it?
So the class hack was a pretty nice ninja move, but obviously you can retrain the model on the single class, and it will start to perform a lot better and make a lot more predictions.
That's
if you go back and merge before train. That could be one way to start, although I know that takes time to train another model. So
that's funny you say. I don't know if you saw this come through the logs or not, but I actually did one earlier this afternoon just in case, but I haven't tried it yet.
Nice.
Let me pull that up. What do you think happens if I screen share on Zoom and I'm also screen sharing on the live stream?
I have no idea.
Okay. Any other thoughts for what I should be thinking about trying next? The thing I was thinking of trying, I think there was on the object zero-shot object tracking, I think I saw some tunable parameters that came from deep sort that were like number of frames that it needs to be present before it gets tracked, and number of frames that it can be missing before it drops the track. Do you think that is something I should tune, or have you played with that?
I think Maxwell said that he carries it through for all the frames. I don't know. I don't know if there's a tunable. I don't know if there's something deeper in deep sort that we could get down into, but there isn't a flag in there right now to experiment with weighting like the distance in past frames.
Interesting. Okay.
Yeah. So it'd be a speed lunk down through the repository, but
Okay.
Could be interesting to check it out.
Yeah, I might try that out. I think I'm gonna do another video infer and just like look at that same player and see why. Like, is the detection disappearing, or is the tracking not identifying the same thing? Like, is he changing too much frame to frame relative to the other players? Cool. You gonna be around for a while if I have more need more scheming.
Yeah. You can always try me on Zoom call. I'll be probably tuning in here for a while. This is getting pretty exciting. Excited that this is live too. This is awesome.
Yeah, I mean, hopefully it doesn't backfire, right? Like the good part is everybody gets to see the debugging. The downside is this might not work. So we'll see. All right.
Hey, nothing interesting is for sure.
Totally. All right. See you, Jacob. Thanks. Okay. Hopefully you all could hear that Zoom call. Jacob had some good thoughts. The first thing that he suggested was to train a model where on just that one class and see if that helps versus taking the output of the other model and hamstringing it into something. So I actually did that earlier. I took Scott's data set, forked it out, and used our remap classes pre-processing step, which I can show you here. So if you modify the classes, it's going to take center, DB, linebacker, quarterback, skill, and remap them all to player. And then when I outputted it, then all of these just come through as player, which is what we did in the hack on the object tracking repo a second ago. But Jacob's theory was maybe if you train the model on that, then it'll do better. My skepticism with that is that the first model was able to learn to ignore these players. If we train this model, I think it's not going to understand like why certain players are visible and certain players are ignored. So I think I might have to go back and relabel and just like label all of the players so that then it has output of the given players. I think that would also do a better job of ignoring the referees, which I noticed they're sometimes getting caught. But I don't have time to do that on the live stream. I think the thing that I might do though is I've got this endpoint here, and let's try and just rerun clip on that, and then concurrently I'm going to check out what the results or what our video inference looked like. Oops. Okay, so I'm going to kick that off in the background. And then if I come back to the visualization, so this was just straight out of the model. So it looks like that player is detected all throughout the way. It's just like there's a couple frames where he goes away and then comes back. I wonder what happens if I reduce the confidence even further from 20. I'm going to try going down to 10 and see what happens with this. So while this is running, I'll do that on another. Oops. I guess I've got my snippets. Check the chat one more time. It looks like there's some inbound. Scott says the model isn't trained for player movement, which is throwing it off. It's only trained on their static stances. Ah, that's an interesting thing. Nice. So I think if I recall correctly from reading through what Scott does, he uses the object detection model to get the initial position of the players, and then uses traditional object tracking via video, I think with OpenCV to track the players. So the approach that we're trying here requires that the players be tracked over over time as they're moving around, whereas the model that we're using is trained on stationary players. So this is a good reminder that the model will learn what you try and teach it to learn. And so since there's no examples of players that are running around in its training data, it struggles to detect them when it's shown things that it hasn't seen before. So that makes a lot more sense of why this is happening. So I think that the right answer would be we should add examples of players running. That seems like too hard to do during this live stream because that would mean labeling a whole bunch of stuff and collecting a whole bunch of data. I think I'm going to keep down this rabbit hole. And I think that what I'm going to try is adjusting this confidence to be even lower. So let's go to 10. Actually, let's go to 10. Oh, you know what? I don't have my key exported here. Let's do this off screen. 1 second. Okay, so I set an environment variable with my, and of course, I pasted the wrong thing. Please don't use my API key. I will revoke that after this. Okay, so this is doing video inference on that, again, with confidence level 10. And then what I save that as visualize 2. Okay, so we've got this over here. So let's see what happens with confidence level 10. I see what he means. So see how when the player's feet are moving like that, and also this is just such a low resolution video. Okay, let's call a quick audible here. So one of the things that Joseph recommended was that there was a data set that I think it was the NFL released. That I wonder if we can combine with this data set and train a new model Although, again, that might take longer than we have here. I hate OAuth because I never know how I signed in. Oh, there it is. So it looks like this data set definitely has plays in progress. I wonder what it's labeled as, though. I'm going to take a quick break here. We'll be back in 15 minutes, and hopefully I'll have a better plan. I'm gonna think on this. All right, we're back from halftime. We had some setbacks in the first half. Our model turns out was not trained on quite the data that I was expecting, which means that our object detection output wasn't suitable for our object tracker. So if you recall, I'll pull up our game plan. So no good plan survives its first impact with the model, I guess. So if you recall, we were taking our video, feeding it to our object detection model, taking the output of the object detection model and feeding it to our object tracker. Well, it turns out our object detection model was trained only on stationary players, but we want to be able to track players as they're running as well. So going to go ahead and basically change our game plan at halftime, and we're going to try and improve this model in order to be able to make the object tracker work. So during the break, I found this Kaggle NFL impact detection project, and I had a look through. It looks like the images are pretty similar to, or at least similar enough to, what we're trying to detect. And I recalled that we had actually written a blog post about this Kaggle dataset and competition. And so I went back and refreshed my memory about what this dataset has and how we used it in the past. And it looks like it was labeled for helmets. And so the players' helmets are what's labeled. I went ahead and downloaded the project, the dataset from Kaggle during the break, and I'm going to go ahead and start hacking away at it. So I verified that Roboflow can import this data format. So I went in here. I'm going to create a new project. I'm going to call this Kaggle football players, and I'm also going to call that players. And to verify, so here's what I downloaded from Kaggle. It's got images, and then it's got a bunch of different labels. It looks like the labels that I want are imagelabels.csv, and then I just grabbed a few images and dropped them into here and verified that what I'm getting looks good. So if I open up one of these, maybe. Let's try that one more time. So it looks like the players' helmets are labeled, and there's certain players that are off the field, certain players that are on the field. Looks like some of these are end zone and some of them are sideline. The sideline look like the ones that I want. So in order to make this more like Scott's dataset, I think what I'm going to do is use a heuristic for how tall the helmet is compared to how tall the player is, and how wide the helmet is compared to how wide the player is, and basically just like extend these bounding boxes around them, and then I'm going to merge these two data sets together and train a model. So I think that's where we're going to get to by the end of the stream today, and then I'll pick up with a part 2 of the stream with that trained model to go forward with the rest of the plan of creating our visualization, since that model is going to take quite a bit of time to train. So that's the new game plan. We're going to update this Kaggle data set to give us the data that we want. I think I'm going to remap everything from helmet and helmet partial to player. It won't work very well for this. That'll be all right. See, it looks like some of these players are, if you're just standing, versus if you're like leaning, probably won't be able to get it perfect, but hopefully that'll be close enough. All right, so let's see. First things first. So I'm CD'd into this data set that I unzipped. Let's get rid of all the end zone photos. So okay, and then let's see how many images we have in there. Oops. So we have 5,000 images in there that are sideline photos. I think Scott's data set, let's see how big that was. Looks like he only had 348 labeled. 448, 500. So let's do about the same. So let's sample 10% of these. I'm going to delete 90% of them. Actually, okay, so I'm going to list the images directory. I'm going to shuffle them into a random order, and then I'm going to take the first 500, output that to imagelist.txt. Let's cat that, and let's make sure there's 500 of them. Cool. So we got a list of 500 images, and then I'm going to make an images to use folder. We do site-wide find or a find and replace on this guy, just to make this into a shell script. So let's say this. Copy images.sh, and then let's do find. I'm gonna do So I'm doing a regex that's just going to take each line and then turn it into a CP, and then I'm going to pipe that into my terminal. What did I call that again? Images _to_use. So I'm going to replace all in this file. So that changed each one of those images to copy that image into my new folder. And then chmod it. And then I'll run it. And then I'll open that in Finder. Got images in here, and there's 500 of them. Okay, cool. So those are the images that we're going to use. So now I've got my labels. What was that called again? Image labels.csv. It's the highlighted one. So let's see. Well, I guess let's go back in here. let's look at one of our sideline ones. And let's just pull this into Photoshop and do some measurements. All right, so looks like this bounding box is, what, about 35 pixels, and the player is about 156. And then how wide is he? It's 156 divided by 35. It's like 4.5 times and twice as wide, and this guy is 36 by 20, 36 by 130. Like maybe 4 times as tall by 2.5 times as wide. Let's give that a shot. So 4 times the height of the helmet and twice as wide. Center it on the helmet, but going down. So I'm going to create a node script to do this. And I'm going to open this guy up next to it. Just grab a few of these. Oh, it's gonna yell at me for that. Use the command line to grab the first 25 lines instead. So we've got image, label, left, width, top, height. I'll blow this up so you can see this a little better. Okay, so I'm going to create a node script that essentially goes through each one of these lines, multiplies the height by, I think I said 4, and the width by 2. Okay. So this should give me however long. So I'm reading in the image labels file, splitting it into line numbers, and then I'm going to see how long that is, and it should match the length of the file just as a sanity check. So should be 19.737. And I need to install Lodash in this folder. And then, what did I call this again? Stretch. Helmets. It's got one extra. I think that's the new line at the end of the file. Okay, so first line is going to be the headers. Let's make this editable. Shift. Yeah. Okay, so for each line, I want destructure this. And then for that last one, that's going to be empty, just not do anything. Cool. Looks like we're good so far. So I just want to map these. So what did I say? I wanted the width to be twice as wide and the height to be 4 times as tall. And then, so the top is going to stay the same. The left needs to subtract the width over 2. I think, to keep it centered. And then I want to join those with a comma to give us a CSV. Okay, so essentially, for every line in the file, I want to grab the column split by comma. I want to move it to the left a little bit by half the width, because I'm going to multiply the width by 2, and that'll keep it centered. And then I just want to multiply with the height by 4. And then I'm going to print it back out in a CSV. And so this should give me a mapped file. So if I just run that again and output it to players.csv. Oh, and also let's change it from helmet to player. Let's do that. Cool. Okay, so I think if we go back into Roboflow, I'm not going to save the old ones that we uploaded. I'm just going to come in here and take our players.csv and our images to use. And we'll see if we did a good job or not on our calculations. And while that's processing, I'll take a look at the chat and see if there's any questions over here. Sounds like somebody's doing a similar project where they detect players' position in a different sport. Has the object detection model been modified to take the different detection relations to each other to predict position? This model I think that's how it's detecting the players, but it's hard to know exactly how. They might have different stances or something like that, but the relative position is something that it should learn about if players are always lined up in the same sort of spot. But you'll have to try it out with your own model. The magical part about computer vision, machine learning stuff, is that it just learns the how, and you don't have to tell it the how. You just tell it the what, and it learns what it needs to know. Okay, so pretty close. Looks like the height could be taller. Looks like almost all of these are not tall enough. Let's try height 4.5x. It looks like the width could be a little bit wider too. I think we're probably going to be better off having these bounding boxes be a little bit loose, because that's what's going to get fed into the tracking. So let's do okay, let's run our script again and do a little bit different math. So So right now I think we need this isn't right. So the center position would have been width So I think this should give us the same results. I just abstracted the variables, and I think we go to the center and then subtract half of the new width, and for 2 it just happened to be the same, but for 3 it wouldn't have been. So okay, so let's just verify that that's the same. Ooh, yeah, not quite, because that's not a string. So I need let's try that again. Okay, 1091, 32. Yep, yep. Yeah. Okay. So those are the same. So now I can change these guys, and I think I want it to be 2.5. And actually, let's go with 5. Let's see what that looks like. And overwrite our players. Let's delete our players new. And then go back into Roboflow and drop these guys in. Somebody in the chat asked if the AI models can work on Raspberry Pi. For example, we trained a model for license plate recognition and reading, and then can it work on Raspberry Pi? The short answer is yes, it can, but it would probably be pretty slow on the Raspberry Pi. I think most of the models will not run on the Raspberry Pi's GPU, so you're looking at like maybe 1 frame per second or a little bit less. I would recommend looking at like an NVIDIA Jetson or a Luxonis Oak device, which will get you GPU acceleration on edge devices. And we actually have some content on that. We're a partner with Oak on the, or with Luxonis on the Oak devices. And we also support NVIDIA Jetson, so it's the easiest way to get going. So if you go to docs.roboflow.com and look at object detection, our edge devices are listed here. So you can see the NVIDIA Jetson or the Oak. And actually, if you go to store.roboflow.com, you can get a discount on your Oak devices. These are a camera that has a built-in accelerator on here, and so you can plug this right into your Raspberry Pi, and this will do GPU accelerated model inference, and then feed the results to back to your Raspberry Pi for you to be able to work with the results in your application. So yeah, definitely recommend checking that out. Okay, so we processed our images here. Let's see if these look better. Looks like some of these could still be even a bit wider. Oh, and see here, the helmet is off because the players are leaning so much, the helmet isn't centered. Let's make him a little bit wider. It looks like the height looks quite a bit better here, though. Oh, interesting that they didn't label all these players either. Okay, let's try this one more time. So width, let's go with 3 instead of 2.5. And then we'll come back over here and drop that in again. All right, not perfect, but good enough. Let's go with that. So now we're uploading these into Roboflow, and what I'm going to go ahead and do once they're there is combine this with Scott's dataset that has the stationary players, and that has much higher quality bounding boxes because they were created by a human versus my simple heuristic of a script. I was taking helmets and stretching them out to see if they can encompass the players. And then, okay, so I've got this one. Let's do, actually, how do I merge these? This one and this one. And we'll call it still labeling players. So where'd we go? There we go. And then we'll go 416 by 416 on this one because that's similar to what we had on our output size. What size was that video that we were going to infer on? Yeah, so that was 452 by 254. Uh, 416 will be pretty good. And then we want to augment. So let's do horizontal flip. Do some cropping. Adjust the color a little bit. So here we're basically adding some variations to these images so that the model learns not to be sensitive to the specific lighting conditions and that kind of stuff. Oops. And then we're going to generate exported versions of all the images. So I'm gonna create maybe 3 each. And this is going to generate all those images of both our dataset and Scott's dataset combined. And then I'm going to go ahead and train a model on that that we'll be able to use and see if that performs better than the one of just the stationary players. All right, so if I come in here, oh, I forgot to remap. So Scott's actually still has the player positions labeled, whereas ours doesn't. Ours here has player and his has the player positions. That's not going to work very well. So let's delete this version. And let's go back and add a pre-processing step for modify classes, and we'll label those other ones as player as well. And try and generate it again. So let's double check. Oh, what do we got going on here? Center. Did we not rename center? Oops. All right, much better. Huh. We should have maybe dropped these ones that were off screen. Let's go back and do that, because I don't want our model to be predicting these guys. So label. Let's see. What's the best way? Let's just label out console.log out what the labels are. Helmet blurred, helmet difficult, helmet sideline, helmet partial. So let's get rid of helmet sideline and see if that helps. So if it's helmet sideline, we're not going to output it, and otherwise we will. And then we'll do the same thing. I'm going to come back over here, and let's delete this project. I'll delete this one too. We're going to re-upload with our new labels. All right, and then let's go find a sideline one that has a sideline and make sure. Yeah, okay, so now these helmets on the sideline are no longer labeled. These are all players. Some of these are going to trip up our model a little bit, I think, but we'll have to make do. We'll see how it does. So I'll upload these again. We'll merge it, and then let's kick off training. There's one image in here with no football players, but it looks like it had offline helmets in it. I'm just going to remove this from the data set. All right, so we're good to go, but we want to combine that with Scott's data set. And then we want to add back our remapping. Player. Then we'll add back our augmentations. What I'm trying to do here is just look at, do these look realistic? Like they could be a real football field with different lighting conditions, different grass conditions, that kind of stuff. Different camera settings. All right, and then let's go ahead and generate a version. Joseph asks in the chat if I'll make the modified labels dataset available on Universe after this stream. The short answer is I need to check the license on this Kaggle dataset that we're using. I can't recall if they allow you to republish it or not, but I think that's why we originally hadn't rehosted it. So one interesting thing that's going to happen to our model here is Scott hadn't labeled the linemen, but we now, in the ones from Kaggle, do have the linemen and all the positions labeled. So I think that might confuse the model a little bit, but maybe it's going to learn actually something interesting, which is when they're stationary and lined up, don't label them, but when they're moving, do label them, which would actually be really good for our use case, because that would let us use the first, n frames of the video where everybody's stationary to identify the important players, and then only track them but we'll have to see how much the model learns. Okay, these look pretty good to train. So I'm gonna go ahead and start training. I'm gonna train from my previous checkpoint. Oops. which was the one that I trained earlier today on Scott's dataset. And that'll just help this train faster. So I think I'm going to go grab dinner while this trains. I'll put maybe 30 minutes on the clock and come back and check in and see how the training run's going. If it looks like the model is going to finish training within that amount of time, I'll keep going tonight and we'll keep plowing forward. Otherwise, I think we'll call it a night after that and call this part 1 of the video, and we'll come back with part 2 to do the object tracking stuff next week. So let's go ahead and put a half hour on the clock. And I'll check back in a little while, and we'll hope that our GPU has happily spun through and given us a train model that we can use. See you guys in a little while. All right, everybody. We're back after our half-hour break where we were going to let our model train. Looks like the training is still in progress, and I just checked the back-end logs. It looks like the model's still improving. So this is kind of one of the frustrating parts about machine learning is that the model's going to keep studying those flashcards until it's learned all that it can from them. And the bigger the data set, the longer it takes to train. So since we increased the size of this data set quite considerably from the first version, it's probably going to take a little bit longer to train. I was hoping that because we started from the checkpoint of Scott's model, that it wouldn't take all that long to train, and was hoping that it would be ready by the time we got back, but it looks like that is not the case. And since it's kind of impossible to predict whether it's going to take just a few more seconds or a few more minutes, or if it's going to take a few more hours and finish overnight, I think from here, let's call it a wrap on part 1 of this video. I will follow up with another live stream probably next weekend where we'll pick up where we left off with this train model and go through the object tracking code again and try and get to that final state that we were shooting towards of a visualized football play from a video. Be sure to subscribe to our channel below and like this video, and if you ding the bell, hopefully you'll get a notification when we go live again, where I can pick up here. Thanks everybody for tuning in. Thanks Scott for sharing this data set and project on Roboflow Universe. It's been fun. I wish we had made more progress today, but this gives us an opportunity for part 2 of the video. And like I said at the beginning, don't forget to check out the first live stream that we did of the Blackjack sample app. We made it all the way through from start to end within just a couple hour stream. And that went through all of the coding for that, of creating a mobile app that you can actually run at the end of it. Excuse me. And yeah, that you can take into a casino and use instead of your Blackjack strategy card. So with that, I'm going to wrap it up. Thanks everybody for tuning in. Have a good night.